Section 1.4 is on page 40. It talks about predicates and quantifiers. The statement x is greater than 3 has two parts. The first part is the variable x, which is the subject or the variable of the statement. The second part is the predicate is greater than 3. It refers to a property that the subject or the variable of the statement can have. We can denote x is greater than 3 by p of x, where p denotes the predicate is greater than 3. And x is the variable. The statement p of x is also said to be the value of propositional function p at x. Once a value has been assigned to the value x, the statement p of x becomes a proposition and has a truth value. It could be true or false. On page, I believe it's on page 41, let me double 50. It's really 56. On page 56, we start with some examples. Example 2 reads, let p of x be the statement, the word x contains the letter a. All right. What are these truth values? Well, you look at the word orange. Is there an a in it? Yes, there is. That's true. There is no a in that. In lemon, that's false. There's no a in true, that's false. But there is an a in the word false. So that would make this a true statement. Now we get to a definition. The universal quantification of p of x is the statement p of x for all values of x in the domain. So the notification, this letter right here, this symbol means for all. You could also read it for any, but we stay away from that. We try to say for all x. P of x denotes the universal quantification of p of x. Here, for all is called the universal quantifier. We read for all x p of x, or for every x p of x. An element for which p of x is false is called a counterexample for all. So if you say all the elements have a's, if you could find one element, just one, that doesn't have an a, that would be a counterexample to that statement. Example 2, this is programming. State the value of x after the statement. If p, then x is assigned a 1, is always 1. That's in programming. So if p is true, you're going to get a 1. And if p is false, you're going to get a 0. Because that's how programming works. You either get a 1 or a 0. This is executed. They executed this statement. Where p of x is the statement if x is bigger than 1. So this really reads, if x is bigger than 1, then you return a 0 or a 1. If the values of x in this statement is reached, when this statement is reached is, if they say x equals 0, well, you notice 0 is not bigger than 1. So since that's a false statement, this is going to yield a 0. B, x equal 1. So in this case, 1 is not greater than 1. We're going to get a 0 as well. This is false. However, in C, you look at C, 2 is greater than 1. That's going to work. Here, you are going to execute x equal 1. And if you're not going to get into the programming, not a big deal. Well, this is not going to work. And this is not going to work. But this one's going to execute because it's true. Number 6, let n be the statement X has visited North Dakota, where the domain consists of the students in your high school. Express these quantifications in English. Well, this says there exists. So, all there exists. So this is some or simply one. So A states some students, there exists a student in the school who has visited North Dakota. You could also say some students in the school has visited North Dakota. Both of those are saying the same thing. So they exist one or some. This one says, remember, this is all. This one says all students in the school has visited North Dakota. Or you could say every student in the school has visited North Dakota. Now, if you look at this, this is the negation of this. Remember that part A stated there exists a student or some students. The negation of that would be no student in the school has visited North Dakota. Or there does not exist a student in the school who visited North Dakota. D. This is the negation of part B. So part B says all students. Here you're going to say something like not all students in the school has visited North Dakota. Or it is not true that every student in the school has visited North Dakota. F. Oh, I'm sorry. E. All students. It's not true that every student in the school has visited North Dakota, or not all students in the school has visited North Dakota. I didn't mess up on D. Did I mess up on D? D was some, so there exists a student in the school who did not visit North Dakota. It seems like I messed up on I explained E for D, but that's what D is. Or you could say some students in the school has not visited North Dakota. And the last, of course, that's all. So you would say all students in the school have not visited North Dakota. Moving to 8. Translate these statements into English where R is X is a rabbit. R is X is a rabbit. Okay, got it. And H is X hops. Okay. And the domain consists of all animals. All right. So in part A, it says, this is all, right? In part A says, every rabbit hops. Or even better, if an animal is a rabbit, then the animal hops. Or that animal hops. B. Remember, this is and. Every animal is a rabbit and hops. C. There exists an animal such that if it is a rabbit, then it hops. And D. There exists an animal that is a rabbit and hops. Or you could say some rabbits hops or some hopping animals or rabbits. So many ways you could say that. Okay, there's a remark which states generally an implicit assumption is made that all domains of discourse for quantifiers are non-empty. Note that if the domain is empty, then when you say for all x p of x is true for any propositional function p of x because there is no element in x. So there's no element x in the domain for which p of x is false. Now, a statement for all x is false when p of x is a propositional function if and only if is not always true when x is in the domain. One way to show that p of x is not always true when x is in the domain is to find one counterexample. So when you say for all or all elements, you just have to find one that's not, and that's a counterexample. Note that a single counterexample is all we need to establish that for all x, p of x is false. And we have a table for that. When you have the statement p of x is true for every x, when is it false? There is an x for which p of x is not true. And if you say there exists there is an x for which p of x is true, it is false. Well, p of x is false for every value of x. So that's a lot of work to do. It's much easier to find a counterexample for all than it is to find a counterexample for some, or there exists one. Then you have to really show all of them. Definition: the existential quantification of p of x is the proposition there exists an element x in the domain such that p of x. We use that notation. There exists an x p of x. This is called an existential. I can never say that word right. Existential quantifiers. All right. And the remark here also, generally, an implicit assumption is made that all domains of discourse for quantifiers are non-empty. If the domain is empty, then there exists is false whenever q of x is a propositional function because the domain is empty. There can be no element in there for which the value is true. And looking at number 10 really quick, it states, let C of x be the statement that x has a cat, d x has a dog, and f x has a ferret. Express each of the statements in terms of C, D, and F, quantifiers and logical connectives. Let the domain consist of all students in your class. All right, all students in the class. So A, all students in the class. Not all. A student in the class. So that means there exists a student in the class that has a cat, a dog, and a ferret. Since it says and, both of those are right. When I look at for all, so we also have a cat, a dog, or a ferret, but this one says or. When it says some students in your class has a cat and a ferret and not a dog. D, no student in the class so there exists no student in the class, a dog and, and lastly, for each of these animals, quantifiers, there is a student in your class who has this animal as a pet. There exists a student in the class that has a cat, a dog, and a ferret. All right. Number 12. Let Q of X be the statement. That's really the same state. If the domain consists of all the integers, which of those is true? 0. Is 0 less than 1? Yes, that is true. Because if you put 0 in there, that will work. And how about Q of negative 1? 0 is greater than negative 2. That one is also true. And how about if I put 1? 1 plus 1 is greater than 2. That's not true. It's greater than equal, but not greater than. And D, there exists an X such that, well, this one is true. Just look at A. That's the first example. For all X, that is, well, this is going to be false. Look at C. If you put a 1 in there, it doesn't work. F, there exists an X such that it is not, what was Q again? That one is true because there exists one. Well, you could look right there. Here it says for all X, the statement is true, and of course that's false because we have some true up there. And anytime you claim all of it, one counter example will kind of throw you off. And let's do a bit more on those. Determine the truth values of the statement if it is true. So here it says there exists an X such that X cubed is less than negative. Well, that is true. Let X equal negative 1. Negative 1 cubed equal negative 1. B, there exists an X. So there exists an X such that this is true. Well, that's true. Let X equal 1/2, a fraction. This says all X, this is true. Well, that is true. No matter what you plug in there, you're going to square it. That will work. But here when you say for all X, 2X is bigger than X, that's not true. Because that's saying X is bigger than 0. So since there's only one counterexample, that's false. Put 0 in there. 0 is not greater than 0. Okay, when the domain of a quantifier is finite, that is, when all its elements can be listed, quantified statements can be expressed using propositional logic, in particular when the element of the domain where n is a positive integer. The universal quantification for all can be listed simply with a conjunct. because this conjunct is true if and only if all of these are true. It's an and. Similarly, when the elements of the domain x1 through x sub n, where n is a positive integer, we know what that word is, quantification, there exists an x is the same as a disjunct, which is one or the other. Because the disjunct is true if and only if at least one is true, that is true. Example 18. Suppose that the domain of the propositional function p of x consists of those integers. Write out each of those propositions using disjunct, conjunct, and negation. Well, let's see. Let me pick a couple of those. Let me look at A. A, it says sum. As in part B, all. So it's not, sum. I'm sorry, sum is or. How did that happen? Sum is or. All means and. Alright, and if I go for there exists some x that are not, so that could be written not p of -2 or part C, there exists, yeah, it's or. There. And if I look at what's the negation of sum, so the negation of there exists some x where p of x is true, so negation of, and again we know that's part A. And lastly, when you say the negation of p of -2, when you say for all, it's and. Alright, last thing I want to talk about would be uniqueness, quantifiers. Do you know that by there exists one, exactly one, the notation there exists one x states there exists a unique x such that p of x is true. Other phrase for uniqueness could be there is exactly one or there's one and only one. Definition. Statements involving predicate and qualifications are logically equivalent if and only if they have the same truth value, predicates are substituted into each statement and which domain of discourse is used for the variables in these propositional functions. So this is the notation for equivalent. Now there is a De Morgan's law which states the negation of this is the equivalent of what's here. And similarly, so whenever you want to show the negation of there exists some, right? Negation, when is negation true? For every x, p of x is true. So you have to show all of them are false. All of them are false. And what is it false? When there is an x for which p of x is true. Now, when you say the negation of for all, that means there is an x for which p of x is false. That is when the negation is true. And when it's false, p of x is true for every x. So, when you say and, that's the equivalent of the negation of each. I'm sorry, you say or. That's the equivalent of the negation of those first and the second and the third. And this is true. And this is the same as all x negating b or p. Express the negation of each statement in terms of quantifiers without using the negative symbol. Well, okay. When you say for all x between 0 and 1, keep -2 and 3. Well, what's the negation of that? Wouldn't the negation of this be anything less than -2 or anything's greater than 3? Isn't that how it works? Because they're saying this is all of them. So how do you write that? Well, exactly as we mentioned, you say, you know what? There exists some x such that x is less than or equal to -2 or x is bigger than or equal to 3, since those are not included. When you look at b, well, the same deal. That's going to be there exists, so you know that's no, there exists some x such that x is here. You're going to say less than 0 or x is greater than or equal to 5. Here, when it says there exists an x between -4 and 1, including both, you would say for all x, x is less than -4 or x is greater than 1, greater than -1. No, 1, 1, 1. I'm sorry, I was looking at E. And if you look at E, when you say what's the negation of that? Well, for all x such that x is less than or equal to -5 or x is greater than or equal to -. And that's would be the end of the section.